Hi, my name is Steph Evans and I'm the lead FEA engineer at Evotech CAE Limited. This video, presented in collaboration with MSC Software, makes up a tutorial from the Apex 101 for Aerospace application series and is focused on a number of model connection strategies within Apex. We're using the Harris Hawk release, highlighting key functionality using the geometry, mesh and associated tools. Some of the connector automation macros have been created for Harris Hawk Service Pack 1. In this worked example, we'll go through the full model development for a typical aerospace assembly, in this case a portion of a wing. This will be focused on a number of different model connection strategies, from glue through edge tie to the many connector types depending on the overall intention of the model. This example is broken down into a number of key stages depending on the overall intention of the model. So the first interaction type we'll look at is glue or glued contact, and this gives us a fast and efficient meshless technique for connecting multiple parts with accurate load transfer across boundaries. This can be used across multiple mesh zones and or mesh types. A description of the underlying Nastran based technology is also given. Then we'll look at the edge tie interaction type, and this is an automated node-to-node interaction allowing parts with dissimilar meshes to be connected quickly and easily based on discrete or global entity selection. The underlying edge tie technology allows complex assemblies with deep product structures to be analysed without having to merge entities into a single homogeneous model definition. Exported Nastran information can respect this assembly level definition through the use of include files. And then finally we'll look at the connector interaction type, and this involves a series of detailed connector types which can be used to emulate the presence of a discrete fastener between parts within an assembly. There are multiple connector types within Apex, spring dampers, bushes, rigid and flexible definitions, which allow detailed load extraction across interfaces. Then we'll look at a Python script which is introduced to automate the connector definition for a real-world example with greater than 700 fasteners in the assembly. Okay, so we'll make a start with the first of the interaction types, in this case glue or glued contact. So looking at the CAD geometry we have in the Apex environment, a simplified representation of a portion of a wing box. So we have a wing skin, front and rear spar and the ribs. So making everything opaque, as it were, so removing transparency, we can see what we have. So the interaction between the spars and ribs at this stage, there's no local detail in the CAD definition, just a simple abutment in terms of the simplified solids that make up the region. So into the geometry tools and mid-surfacing. So we're going to turn the three-dimensional solids into 2D surfaces using one of the mid-surface options, and we're going to auto-assign thickness. So just a global sweep across the geometry, and that will develop the mid-surfaces along with the thickness property, or thickness and offset property that's required for subsequent meshing and analysis. So taking the solids out of view, and we can show the mid-surfaces again. Putting the vertex or the vertices into view, and you can see there's a gap between the, in this case, the front spar and the rib, but when we show the 2D equivalent thickness, we've still got the abutment at the joint definition. So wing skin back into view, show only on the wing skin, and we're going to mesh the wing skin with the typical element edge length, so 50mm in this case, using the default mesh parameters. And you can see we've got a nice regular quad mesh that appears for that mid-surface, and then going through the additional members, so the ribs and spars, and meshing those with different element edge lengths. This is just to demonstrate what happens when we mesh individual bodies with no reference from one part to the next. So we can see here we have a physical gap between the mid-surfaces and also no congruency in terms of the mesh, so where the spar meets the rib in this example. But if we put the 3D display on, we can see the abutment which we're trying to capture within the model definition. So measuring the gap So in this case, from a point on the spar to the rib plane, or the rib surface, about 2.5 millimeters, which ties up with a thickness of 5 mil, and then putting the wing skin into view. And if we zoom in on the mesh definition, we can see there's no congruency again. So the various interaction types we've got, so showing some of the options here, but in this case we're going to use the glue contact. So to type in the glue pair tolerance, 5 millimeters in this case, so we want that tolerance to be bigger than the gaps within the models. And you can see just a global sweep over all the entities in the model. Apex recognizes the abutment between one component to the next and develops the glued contact as shown by the pink and grey entities, depending on which side of the contact interface we're looking at. And if you look in the model browser tree, we have a unique glue definition for each contact pair, and we can cycle through the tree structure. So in this case we've got the innermost rib connecting with the wing skin as one glue definition. So we can look through the model and see exactly which entities are connected to one another. So next rib along, rib to wing skin, and we can just cycle through the model and view or edit the contact patches as required. So full control of the display within Apex, and we can turn all of those patches on. The glue patches are discrete entities, so we can use the cursor selection tools to pick those glue patches direct from the screen rather than the tree if necessary. But in this case we're working from the tree explicitly. So defining the material, rather we have a material already defined within the Apex database, and then assigning that for the full structure. So it's a 7075 aluminium property isotropic material. So if you remember, we had the thicknesses defined from the mid-surface definition. We now have properties, material properties defined, and putting in some simplified loading in the structure just to show how the loads transfer across the glued interfaces. So glue contact is a good technique. It's very quick to tie similar meshes together to allow us to do sort of what-if studies or trade studies. So fixing one end of the wing and then applying an enforced displacement on the other, the opposing rib. In this case, we're going to put a vertical displacement of 2 millimeters enforced onto the overall wing box, just to show the again the response based on that glue contact and load path introduction through the assembly. So just finishing off some of the enforced displacement definition, and we should be pretty much good to go with the loading and the subsequent analysis. So we can see that 2 millimeter vertical displacement in the model there. Okay, so ready to go. So we can set the analysis job up, go into analysis readiness, and we can see the only warning is to do with unmeshed geometry. So we're absolutely fine in terms of the analysis. So in this case, we've got a number of different options: normal modes, static, dynamic. But in this case, we're going to look at a buckling analysis. So we've got the standard output requests, and Apex will handle all of the load application, the preload, and the buckling calculation as required. So just running through the analysis very quickly, and then going into post-processing, and we can see, first of all, based on the buckling modes, so you can see we've got a first buckling mode here, which is the lower skin, but we're more interested in some of the beta bay rib buckling, which in this case is the third mode. We can see the displacement, just cycling through this displacement. Yeah, we can see the mode shape that's developed, and we've got the load factor defined for that buckling mode. Again, very quick to set this model up based on the glued contact, and we can see we've got the various different mode shapes along with their buckling factors available to allow us to make an assessment on the appropriateness of the structure. So what we'd like to do now is just understand if we were to make a change to the architecture of the wing box, so maybe changing thicknesses or rib layout or spar layouts, what the structure will do. So again, showing that we have no mesh congruency, we have the glue contact defined. We're going to change the mesh for the full structure and understand what impact that has onto the global buckling factor that's calculated. So again, we've simply remeshed all of the entities. We don't need to redefine the glued contact definition. You can see there that there's an incongruent mesh at the interface, but because glued contact is a meshless connection type or interaction type, it doesn't concern us that the meshes are not congruent. And again, we can just run through the model checkout rather, and show that the glued contact definitions are still intact. Loads and boundary conditions intact. Again, the generative nature of Apex means that a simple remeshing cycles all the way through the model, so we don't need to redefine properties, material definitions, loads and boundary conditions, or even the glued contact as highlighted in this case. And again, 3D shell thickness displayed, so showing the full model, and then going into analysis readiness again, or setting the job up, and we can rerun the buckling case. And again, very quick to rerun. This isn't a particularly large model by any means, so the buckling solution happens, well, not quite real time, but we're only talking a number of seconds to run this structure through. So very useful to understand mesh sensitivity, and in a moment we'll look at layout sensitivity as well in terms of the rib placement. So looking at the buckling factors again, and we can see for the third mode we now have a very similar eigenvalue or buckling load shape, and showing the displacements and cycling through again. If you notice that the load factor is now slightly different based on the fact that we now have a finer mesh definition, effectively more elements to capture that buckling mode, and therefore more accurate solution. So just looking at the slide illustrating how mesh size or mesh sensitivity will affect the buckling response. So on the left hand side, with a coarse model, the buckling factor is calculated at 2.13, and on the right hand side with a much finer mesh, the buckling factor is calculated at 1.92, which means that a reduced load, 11% lower, is required to buckle the finer mesh panel. And again, so glued contact is a meshless connection allowing for ultra rapid mesh sensitivity studies, and the generic framework, or generative framework I should say, as the mesh is changed, all downstream definitions, so mesh, glued contact, materials, properties and other boundary conditions are updated, so minimal input by the user to understand how the model is going to respond. So we've seen the impact of mesh density on the model response. So now we're going to look at a layout change, or layout sensitivity. So this will involve moving the rib definitions, so we effectively shorten the critical panel dimension. So we're going to simply copy the three outermost ribs by half the bay distance to give us intermediate ribs in that assembly as well. The overall intention here is again to show that because of the meshless nature of Apex, we can quickly tie things or glue things together. So because the ribs have been moved, we now need to split the front and rear spar to accommodate the new connection at the spar to rib interfaces. So we can see here, split the inboard spar, and repeating that for the next spar along, and just cycling through the model just to give us the cuts as we need them. And again, just picking very quickly those model edits. And again, generative nature of Apex means that as the structure is split, the mesh is updated along with all the property definitions, the material definitions, and any loads of boundary condition that was on there. We could redefine the glue in this manner if necessary, as we're about to show. Just double checking the sections. So some of these sections need to be updated because the surfaces have been split. The generative washdown, if you like, in terms of the materials and properties will work for common surfaces, but however, if a surface has been split, then we need to redefine those sections, and you can see there using the section display it's very straightforward to make those updates. And again, if we look at the 3D thickness plot, you can see the way that the surfaces abut one another in a similar manner to how we looked at for the original rib layout definition. So just viewing some of the glue patches, so we can see here, because we've split the front and rear spars, we have now lost some of the glue contact definition from those new cuts within the spars onto the wing skin and the ribs. So we're just going to update the glue patch definition, just a global sweep to pick all the entities, and then based on the original tolerance that we used for the original layout, just make those changes. And you can, again, Apex is just cycling through and understanding how pairs are connected based on those tolerances, and then just very quickly defining the assembly level definition. Again, the meshless technique. So there are some glue patches which are now redundant based on the legacy layout, or legacy topology, if you like, with the model, so we can just quickly delete those. Apex has flagged them as being redundant, and then just viewing the newly created glue contact pairs, we can see everything is defined as we want it to be. So now it's a case of just double checking the loads of boundary conditions, and again, we haven't made any splits on those surfaces, so they're good to go. We haven't needed to redefine any of the material definitions. Again, model ready to run. Only a warning on unmeshed geometry from the original solids we haven't used. Running the buckling case again, and then we should see the model response very quickly, and solving in seconds for this relatively simplistic model, just to illustrate the glue technology. Going into post-processing, and again we can see now that we have a bay, the inboard bay buckling mode is now a different mode, so first order mode rather than a second order mode that we saw previously, showing a fringe plot of displacement rather than stress or strain energy, and we can extract the appropriate buckling factor for that portion of the structure. Looking in the table of buckling factors, we can see how those changes have affected the overall model. So in this slide we can show the effect of the rib spacing modification. So based on a trade study we may have been asked to look at, the critical mode for that portion of the wing skin, on the left hand side with the original rib spacing we have a buckling factor of 1.92, and then on the right hand side with effectively half that rib spacing, so a much shorter panel or much narrower panel, we now have a critical buckling factor of significantly more, 2.56, in terms of the load that's required to buckle the panel. So good example here of how the Apex generative framework allows us to develop ultra rapid trade studies for downstream assessment. So just to recap how glue contact works effectively under the hood. So a very straightforward way to set up the glue contact for dissimilar meshes. We can control, edit and view the contact pairs as required, based on a series of auto or manually defined pair tolerances, which are available through the form definition. The way that Apex works, or the glue contact works, is that the solver, whether it's the internal solver or the external Nastran solver, the solver sees the glue's contact as a logical set of multi-point constraint, or MPC equations, between glued bodies, and that allows accurate force and moment transfer at the interfaces. It's possible through an external run to convert glued contact into those multi-point constraint forms, as shown in the Nastran deck definition on the slide. But the way that the MPCs work, effectively explicit MPCs, which connect the nodes between adjacent glued contact pairs and set the terms for the explicit MPC to allow rapid or accurate load transfer at the interface, irrespective of the dissimilar mesh at the glued contact pair. If we look at some of the load transfer effects for glued contacts, so in this case we're looking at comparison between a fully solid cantilever beam modeled with hex elements and then a hybrid shell to solid glued contact definition, so that the mid portion of the beam is replaced from a solid to a shell representation with glued contact, so that gives us accurate force and moment transfer at the interface, and we can show that we've got equivalent shell thickness. Running the analysis, we can see that we've got equivalent stiffness in terms of the displacement of the two approaches, and also equivalent stress distribution for the two approaches. Now this has significant impact on the submodeling strategy, which we'll come on to in a later tutorial. So moving on to the second interaction type, this time the edge tie, and using a similar assembly to the one we looked at for glued contact, taking the solids, mid-surfacing, developing the auto thicknesses, hiding solids from view, and we can see the surfaces as generated along with the free edges shown in red. So at the moment none of these entities are connected together. I'm going to look at some of the edge tie technology and how that can help us with the assembly. So mid-surfacing, there's a physical gap between discrete parts, obviously because of the mid-surface effect. So we're just going to measure some of that gap first of all between the skin and the substructure, and then between the spar and the rib webs or rib planes. So 2.5 mil shown here as per the solid thickness. So we need to understand these physical gaps because we're going to extend surfaces together so that we can generate a congruent mesh across the full region. So first of all, we're going to look at the standard connection definition, whereby we've moved all of the surfaces into a single part. So if you look in the user the model tree, we now have all the entities within the skin, and then we can extend surfaces together using an effective tolerance based on the gap we measured previously. And now all the surfaces are snapped together, and we can see the yellow lines show where we've got shared topology, and a resultant mesh will give us nodal connectivity between equivalent bodies. However, we've lost the assembly definition for the structure, so we're going to undo a couple of steps and go back to the original part within assembly definition, and we're going to do the same extend operation again, where edges are snapped to adjacent surfaces or faces, and we can see the gaps have closed, but we've still maintained the model assembly architecture. We can see that by virtue of the colours and how they match up with the browser tree. So once we have the surfaces extended, we just need to do some quick splitting to ensure that we've got edges, in this example, edges for the spars that mate up with the underlying rib plane definitions. So just running through some of those splits. So we're using the split tool to break using surfaces into discrete parts rather than partitioning. which we'll look at in a different example. So we're just running through, and we can see now we've got the spars, front and rear spars, split into discrete parts representing each particular rib bay. Made a mistake here, so we've split one of the ribs, so we're going to extend those back together so it's a single body. Now we've got the full surface definition broken up into the discrete parts or bodies within each discrete part, and then therefore the subassembly, and we can then mesh the surfaces accordingly. And we can see, if you look very closely, that we don't have nodal connectivity between parts. Even though the edges have been snapped together, the meshes are flowing across those edges at the moment. So we're going to look at using the edge tie technology to bring those edges together such that we've got node-to-node connectivity at the interfaces for each part within the assembly. So I think we're going to just look at some of the local change here. So we're going to the hybrid quad tri mesh for the ribs, given the slightly irregular shape, but the rest of the structure is quad meshed based on the simple surface geometry. So going into edge tie, and we're going to use the discrete method in this case. We've got a cleanup tolerance. So basically pick all the faces, middle mouse button to accept, and then pick all the edges, and again middle mouse button to accept. So minimal, well, no keyboard access required in terms of this operation, and that will effectively snap all of the edges together so that we've now got a congruent mesh definition at all of those interfaces. So we can see there, certainly between the spar and ribs, how those edge ties have worked. If we look in the model browser tree, we can see a discrete edge tie per body pair, as it were, similar to how the glue contact works, so we can cycle through and understand what's going on. Checking the element quality, so we can isolate and enhance and show any areas where we have invalid elements. So if we look at the edge or the back edge of the rib to skin definition or the joint, we've got these vertices which are slightly overextended based on the original mid-surface definition. So it's a quick case of using the vertex edge drag tool to snap those vertices back into position. We can do this by splitting geometry, but just wanted to demonstrate again how the generative nature of Apex works in this manner. So we're moving the geometry, which in turn moves the mesh. All of the underlying properties and material definitions are maintained, so it's literally just this single one mouse click operation to fix each one of these discrete regions. And again, we can see in the browser tree how these invalid elements are defined, and as we work through the model, the mesh quality is updated in a real-time sense, and all of the invalid elements disappear from the model definition. So just finishing off the last one here, and we can see now that we've got no invalid elements left, but we now have some poorly shaped elements. So if we look at those, plot just the poorly shaped elements and extend once so we can see what's going on. So we've got a slight overhang here in terms of the skin relative to the rib. So again, I'm using the vertex edge drag tool again, snapping the skin edge onto the rib web. Again, single operation, and that updates the mesh quality and removes all of those poorly shaped elements in a single operation. And that's finished. And if we look in the element quality fringe plot, we can see that we now have no invalid or even poor elements for the model definition. So geometry edits made, mesh edits made. We can now check the connection topology. So standard free edge check, but now we can look at the free, shared and manifold edges based on the edge tie technology. So now we have the yellow lines which show shared edges and green lines which are yellow which are manifold, and then yellow with green which are shared edges. developing the model further, so this is a real-world example now where we might want to understand the load going through a given joint or a given region, maybe develop the free body loads across one of these discrete parts within the assembly. So we're going to introduce some one-dimensional beam and spar flanges. So we quickly mesh those regions, and we can see the bar element definitions. And now we need to define a section. Well, first of all, we're assigning a material. Now we've got the all of the mesh 1D and 2D entities complete. So material assigned, and now we're going to look at one-dimensional beam properties. So first of all, we need to define a section definition. So we're calling this flange. And we're putting in some rectangular properties, so a width of 50 millimeters and a height of 5 millimeters for that section. You can see the dimensions are updated accordingly. And now we need to relate that section to what Apex calls a span, which is effectively the relationship between the section and the 1D meshed entities. So we can control things like offsets and orientations. But by default, Apex understands from the baseline geometry the best way to orientate the shape or the section. So we're just running through that for the rib flanges, and we can see the three-dimensional update in terms of 1D beam display, and then repeating that for the front and rear spars. So again, just setting the name, picking the shape, and then specifying the area of the model where that shape is to be applied through the span definition. And again, as we apply those entities or the shapes, the 3D display gives us real-time feedback in terms of what's going on. At this stage, we could manipulate the shape or section orientation and or offset, but we've got no offset or orientation changes to be made in this particular example. Again, so just finalizing that for the rear spar, and now the model is complete in terms of the 1D beam element definitions. Okay, so very quick to perform all of these operations as it is with pretty much everything in Apex. And then we can just double check the layout in terms of the rib, spar and skin overlay. Now the model is complete, so we're going to apply some simple loads and boundary conditions. So the inboard end of the wing box we have fixed, so all degrees of freedom clamped in space, and then we're going to put an enforced displacement to act on the outboard rib web, as it were. So specify the region where the displacement is going to act. In this case, we're using a rigid connection, so the whole of that region will see the same displacement. We can use a compliant RB3 type definition if necessary. So moving the triad so that the enforced displacement acts at the center of the rib, centroid of the rib web, and then putting in a vertical displacement of 2 millimeters, which we're again enforcing to give us an upward wing bending action for this simple example. So again, very quick to apply these loads and boundary conditions to the model. So once we've got those defined, we can place in the analysis scene, do an analysis readiness check, and this gives us if there's any potential errors or warnings for the model. And we can see we've got a missing section. So we go back into the model, and from sort of prior knowledge, we know that we potentially have a problem with the spars when they were split. So looking at those regions and going into section view, we can see that the grey areas have no section defined. So it's a simple case of redefining the spar property for the full region, and then going back into the full assembly, and then running the analysis readiness check again. And we have no warnings, no errors. We've got warnings for unmeshed geometry, but that's just from the solids that we defined. We haven't meshed in the model. output forces for that given load case, or output request I should say. So we're going to specify element forces to give us some visibility of what the structure is doing, and then just running through the analysis. So while the model's running, we'll just have a quick look at the nodal connections defined for the edge tie. So on the slide we can see that the model, or the Apex product structure, is broken down in the left hand image, and we've got again the skins, ribs, spars defined. And on the right hand side we're showing what the edge tie is doing under the hood, or internally if you like within the solver, or via an external Nastran run. So we basically have a number of zero length bar or R-bar connections which are rigid connections which connect discrete nodes for each edge of the of a given part, and tie them together so that we have full load and full load transfer across the interfaces, but we still maintain discrete nodes per part. And this is important because it allows us to understand what the model's doing from an assembly perspective. If we were to write the model out, and again using the standard Nastran deck export, we can see in the left hand image, which is controlled from the model browser tree, and we can write out the model as in terms of what Apex calls as a hierarchical model file. So we have include files for each part within the assembly, and then we can connect those parts together through R-bars, again the zero length R-bars, which means that we've defined the model still within its subassembly architecture for downstream analysis. So with the analysis complete, we can go into post-processing and start to understand what the model's doing from a load transfer and free body perspective. So first of all, just double checking the global action. So this is a wing up bend case, and we can just show some of the simple displacements to marry up with our understanding of that case. Quick animation just to show what's going on. So we can see the bending action will put the top skin into compression and the bottom skin into tension, and that should be verified through the load transfer that we see for each discrete part. So first of all, looking at the top skin again, so understanding the shell element forces. So in this case we're looking at the force in X and using a local system to control the X direction. So X, the red vector, marries up with the spanwise direction, and we can show for those shell forces the max and min values. So the red highlighted in the max highlighted in red and the min highlighted in blue. So we've got again compression on the top face and tension on the bottom face based on this local system. We can edit the system if required to rotate or translate based on the Cartesian definition, or we can look at this in a cylindrical or even spherical system if necessary. But we're taking the default Cartesian system for this model output. So now looking at the ribs, so we've still got the hotspots displayed for the skin interface with the rib. So now we're going to look at the attachment forces, which are effectively the loads developed across the edge ties for these given regions. So you could think of these as free body loads acting on the ribs. And if we show a scale plot in that local system again, we can see the interaction between the spars and the ribs due to that wing bending action. So again, we're looking at a local system for the X component, giving us the spanwise action, and that marries up with the standard wing bending response that we would expect. So the final interaction type that we'll look at are connectors within Apex, and we're looking at a simple example of the major subassembly to start off with. So first of all, the different connector types available in Apex: springs, dampers, spring dampers, and C-bushes, which are effectively a subset, or a master set rather, of spring and damper definition, where you can define stiffness and damping in 6 degrees of freedom. Then we've got rigid links, whereby we can specify 2 ends for the link, And then finally a flexible connector, which is often used to model a fastener, and here we can input a fastener name, a diameter and a material for the fastener's definition, again specifying some of the end constraints or end connection types that we're using, rigid or compliant depending on the model topology. So looking at the example, we have the rib to spar definition, so we just select the two edges that make up the holes and the fasteners created based on the dimensions that we've specified. So we can toggle the fastener view on and off either from the icon or from the tree. We can go into the tree and modify the fastener definition. So by default we've got a rigid connection, but we're changing that to compliant, or an RBE3 connection between the end of the fastener and the hole that it's attached to. So we can repeat that for all of the interface fasteners in this region. So again, Apex calculates the center of the hole and generates the fastener between the two center points for those holes in the connector definition. So again, very straightforward and visible within the model browser tree, both in terms of viewing and or editing. So for clarity in terms of what Apex is doing. So in this particular example, we've defined those connectors as we want. We can look at the shell thickness, that's unchanged based on the fastener definition, and then we can look at potentially remeshing the structure. So in the area where we've got those fasteners defined, perhaps not the best quality mesh, so we can reduce the element's edge length, and we've got a feature mesh setting turned on so that we get a nice ring of elements around each fastener, so perhaps a bit more appropriate in terms of looking at the load and the stress distribution around the fastener hole. Check the quality, or rather the thickness first of all, and then the quality. So again, the generative nature is washed through the model, so a simple remesh, we don't need to do anything else in terms of the fastener connectivity. It's maintained through the definition or any edit to the model. So a different approach here. We're now going to look at, rather than hole-to-hole fasteners where we've got the hole explicitly modeled, we're going to look at point-to-point type fasteners. So first of all, we're going to defeature both the rib and the spar in this region, and then specify our defeature dimension. So with a value or diameter less than 20 millimeters, it's selected a number of holes in the interface location, so it's picked out some holes on the left hand side which are involved in the original hole-to-hole fastener definition, so we don't want to defeature those, so we can simply deselect those from view or from the defeature operation so that they don't get removed, and then once we're happy with our selection, so it's only the holes on the right hand side that are going to get removed, middle mouse button to accept, defeature takes place, and we've got it set such that we create a seed point at the hole center. So we've now got our model and mesh topology set up in such a way that we can create our fasteners. So again, back into the connector form, and again very similar, flexible link, so we're picking point to point in this case, so the blue point is the rib and the magenta point is the spar. Again, so auto execute turned on so that we can quickly cycle through the model definition and create the fasteners as required. And you can see in the tree, as we create those fasteners, the fastener list is populated, again for viewing control and or editing, based on the standard Apex definition. So a simple load case, just putting a tension load across the local assembly, and we can see the lap shear effect as the tension pulls the rib into the spar, and then turning off displacement, we can start to look at the interface loads, or rather the fastener loads that are developed. So going into the results browser tree, so set the connectors as the plot target, and then we've got full control of the connector forces and or moments, and we can plot the vector value on a resultant or component level based on the load that's transferred through those fasteners. So again, we've got scaled views turned on, so we can see the larger vectors defined. If we set it to uniform view, you can see the lower values that are attracted to each one of those fasteners, and we can animate and cycle the load through to see how those loads are being distributed through the joint. And going back to section view, scaled view, again based on the local Z definition or direction for the fastener, and we can show the labels to give a magnitude of the load as we might need for downstream sizing or modification. Okay, so very quick to create and flexible to post-process as well. So looking at the full assembly now, so in this particular example we've got upwards of 700 fastener pairs, so obviously that would be pretty laborious to define based on the manual approach we've just looked at. So first of all, just throwing a relatively fine surface mesh onto the full assembly, and we've got the feature mesh settings defined such that we get a nice definition around the holes. So we've got this ring of elements turned on, so if we hide the skin from view we'll be able to see that better for the rib to spar definition. So good quality mesh transitioned into those ring of elements around the holes. So this gives us the starting point for the downstream fastener definition. Changing the skin colour to white just to make the next operation perhaps a bit more obvious. So what we're going to do now is look at a macro that's been developed to allow us to highlight holes, highlight the hole centre, find an adjacent hole within a given tolerance, and then build the fasteners around those hole pairs and doing the connection. So run the macro and we see a summary of what's created. So we've got 744 fasteners developed. So again, very quick to do that with the macro, or the Python API based macros within Apex. I should say that at this stage this macro was developed for Harris Hawk Service Pack 1, so you need to bear that in mind based on what version of Apex you're using. So again, into the model browser tree, and we can see that each connector that's been created is named based on the component pairs used in the fastener definition. So we're looking at the rib to skin fasteners at the moment, so putting those fasteners on, or in view rather, and then looking at the discrete rib itself. You can see the connection from the fastener through the rigid spider into the rib mesh topology. Again, so very straightforward to create those, or to view or edit as required. So turning all of those fasteners back on into view and performing some post-processing. So we've actually run this already, and looking at some of the output, and we can see again when the model comes through. So we've got the mesh topology, the element edges turned off, so we can see the connectors are displayed in the post-processing environment as well. So we've got a good handle on what the pertinent directions are in terms of shear and axial force, setting the connections as the plot target, and then we can start to look at the vectors as they come through in terms of the joint interfaces. So just changing some of the output, or rather visualization parameters, and then showing the labels to pull out the peak loads for each one of the discrete fasteners in any system or any component direction that we're interested in. So again, repeating this exercise, but you saw there we had to use pretty fine mesh. We could transition away from the fastener region, but we just used a single element edge length for the full model definition. In this particular example, we're using a much coarser element edge length or mesh size, and we can see that we've got some pretty poorly shaped elements around the holes, given that they're still captured within the geometry. So we could again perform a manual operation. We could defeature the holes and then create the fasteners manually, but again for 744 fasteners that would be pretty painful, to be honest. So we're setting this up in such a way that we can develop the fasteners on what we call a point-to-point basis. So we're going to defeature the holes and then create a fastener between the the center points of those holes to tie the model together. So just going into macro again and picking a second macro, which is the point-to-point macro. So running this for the full entirety of the model. The macro runs, it's finding the center points, defeaturing, and then building the fasteners based on a proximity search between the center points of the holes. So again, pretty quick way to build this for all the fasteners that we've got. Bottom left hand corner, we're seeing instructions of what's going on in terms of the macro, and again 744 fasteners built in a little bit more in the blink of an eye, but pretty fast as you can imagine. And then going to the connector form, and again we've got the pairs used in the joint definition to define to name the fastener. So just showing the rib to skin fasteners again, putting the ribs into view. See the resultant topology. So the defeaturing exercise as part of the macro has given us a much more regular mesh definition for far smaller model in terms of the node count and degrees of freedom. So this model would run much quicker than the original model with the fine mesh definition around the fastener holes. So taking the fasteners out of view, checking element quality, so we've got no invalid elements in this case, some local poorer elements around some of the fasteners, but nothing that we're concerned with in terms of the way the model's going to run. Okay, this could be run in a similar manner. So looking at the output for the hole-to-hole versus the point-to-point definition, for the hole-to-hole model we've got an element edge length of 5mm to give us the good quality around the element holes, around the fastener holes I should say, and then for the point-to-point model we've got an element edge length of 20mm, so a big difference in terms of the model size and overall node and degree of freedom count. Looking at the von Mises stress, just as an overall guide in terms of what's going on, you can see that there is some subtle change, certainly in terms of the inboard end where we've got the peak value shown in red. The way that the stress flux flows away from that region is subtly different. And then if we look at the discrete regions, so on the left hand, well, the two left hand images are again showing peak von Mises stress. So the hole-to-hole fasteners, the peak von Mises stress is 62.7 MPa versus 30 MPa for the point-to-point approach. Now some of this will be due to the flexibility built into the fastener definition by virtue of actually modelling the hole, but some of it will also be brought in by the fact that we have a much coarser element edge length for the bottom image. On the right hand side we have for the hole-to-hole fastener the peak fastener force resultant, that is 2.51 kilonewtons, and the bottom image, which is the point-to-point fastener model, is 1.94 kilonewtons. So again, a subtle difference in the output, or maybe potentially a significant difference in the output, but the user would be advised to use an appropriate downstream joint de-idealization methodology to ensure that whatever loading effects are captured in the joint calculation. Okay, thanks for watching this tutorial, and I hope you found it both informative and interesting. I'd like to say a quick thank you to Larry Pierce and Stefan Ternelius of MSC Software, who helped out with the generation of the fastener automation macros. Be sure to keep an eye out for the remaining tutorials in the 101 series to illustrate how Apex can help with your FEA process.